All right, let's go.
Avoid now you're no more these same things.
All right, let's go. Right, here we have temperature. Temperature must be in Kelvin, don't forget that. Here we have pressure, here we have volume. They want to get a number of moles. So which formula are we using? PV is equal to nRT, N is equal to PV over nR. Sorry, RT. So PV is equal to RT. Pressure is equal to 2.4 by 10 to the 6. Volume is equal to 5.5. Everything in the right SI unit, right? R is 8.31. And the temperature is 25 plus. That's 25, Darren. 273.15. Please don't add 273 as 270.15, right? Work it out, tell me what you get, please. How much will I get? 5, 3, 2, 7. So much more? I just make up a number. Yeah. Right? So yeah, so the number of moles is 5327.8. Wrong equation.
Yes.
It's not wrong. Sometimes what happens is when I write it out, I should type it, she's typing wrong. Like you want to 0. Right? Next one, they gave you the number of moles, they gave it temperature, they gave it pascals, and they want you to find the volume. So which formula are you using? Same thing, right? But you just rearrange it. PV is equal, this is number 2. PV is equal to nRT, and I want to find for P. So that's nRT on P. I don't have much room, right? But just plug in the values and some more again. 2.94
times 10 to the minus
10 to the minus 4. Which kind of all the errors in the equation?
somewhere it's something for that
What's that? Pure math, are there errors? In the pure math? Yeah, I'm not really good at it.
You know, every class will be like, oh, if I'm mistaken, I just don't.
Which one?
Every class will say that.
What happens when they edit it? I don't have your now. Huh? Alright. I'll send you next one. You check that one. But the new one's good. The new ones are something all those okay. Right. So that's PV is equal to nRT. Nice. Right. You all remember the kinetic theory of gases?
Yeah.
Particles always moving randomly. Each molecule is identical. Collisions are elastic and so on, right? Right. So you have to learn all of these, right? But what's important today is that we need to be able to prove that PV is equal to 1 to mc squared. I want to explain this c squared here. Right? Here's what has happened. In real life, an object can move in 3 directions. Right? An object can move in the x direction, it can move in the y direction, or it can move in the z direction. Right? You all remember Pythagoras theorem?
No.
Like if you have these two here, the resultant is what? The square root of, let's say that's a and b. A squared plus b squared. Right? So the same thing applies in 3 dimensions. Right? Same thing applies in 3 dimensions. So in 3 dimensions, c squared, right? C is like the average of all 3 directions. C squared is equal to x squared plus y squared plus c squared. Right? So if you're moving in any other directions, your average speed is this. Right? What you see in here, that symbol is called that symbol is called mean square. Right? Speed. So what you're doing is you're taking your speed, you're taking all the speeds, you're squaring them up to. And then you're finding the average. Right? So that symbol there is the mean square speed. Sometimes I write it like this, sometimes I write it like that. Okay? They both mean mean square. So you're squaring the speeds and then finding the mean. If you have 3 speeds, you square all the speeds and then you find the mean of it. That's for this thing here we're going to try and prove.
I wanna do that.
Alright, so we need to be able to prove this. Everybody want to come and try it?
Yeah,
The whole thing?
yeah, sure, try. Yeah,
You know
sure,
that?
like that.
Alright. Alright, so let's take a look at it. I'll use the handout for now because the handout will give you a little idea what's going on, right? So we are trying to get PV is equal to 1/3 NM mean squared. Alright? We already know those 2 and 4 there. PV is NRT and PV is NKT. Right? We're going to use those to help us. Right, so let's consider gas, right, in a cubic container of site L. So watch it there. A cubic container, each side is L, right? Let each of the n particles have a mass m. There's n particles in there, each has a mass m. Right? We are only going to focus on one particle. So initially a single molecule, which is moving towards wall A1. And suppose that is they give you the x direction of velocity. So what are they? That particle, right? Remember, that's just one particle, that n of those. So we focusing on one particle moving in one direction. Ideally, we have n particles moving in 3 directions. Right? X, Y, or Z. Okay? Right. So let's get down to the physics side of it now. What would happen when that particle hit the wall? It will exert a what?
Force.
A force, right? F equals ME, right?
Yeah.
And when it exerts a force on an area, it exerts a what? Pressure. Right? So here's what we're trying to find. We are trying to find the pressure exerted by one particle in one direction. Right? When you find the pressure exerted by one particle, we assume all the particles are the same, right? We can find for n particles. That's okay? Technically, just multiply by n. Right, Arian? And no? Where you lost it? Pay attention. I realize. That's not important. Right? So when one particle hits the wall, it will exert that pressure. We're gonna try to find that pressure. And then since we have n particles, we multiply that pressure by n. Is that okay? And then remember, we're only considering one direction. Then we have to consider what will happen in the y and z direction, right? So we're going to try to consider all 3 directions after. So we're considering one particle in one direction, then all the particles in one direction, and all the particles in 3 directions. That's okay? And then we will develop a formula for pressure exerted by all the particles hitting the wall. That's okay? All right. This proof is something that you have to be able to do. So what I want you to do is just sketch a diagram. And we're going to do it together. Sketch a diagram. I know it's in the handout, but sketch a diagram. And we're going to try to do this proof together. Unit piece by piece. Right? Just put a cube of length L and so on. Ready? Right, so we're gonna go through it step by step. But let's have a little diagram so you'll be able to know what's going on, right? Ready? Alright, so let's go through the handout first and then and then you'll guide me along how to do it here because sometimes you will see, please prove this, right? Whole thing become an exam. Right, so I want to make sure you can do this. Alright, let's go. Right, so first thing first. This molecule will have an initial momentum of m by vx. That makes sense? Yeah, the mass is m and the velocity is vx. In the direction towards the wall. When the molecule collides with the wall, the collision is elastic. What elastic mean again? Right, and it conserve momentum, conserve. And it will rebound with the same speed. Right, so now the momentum is minus vx. Right? That's right. Are you okay with that? So it has the same momentum when it bounces off the wall. So therefore, what is the change in momentum? Mvx minus mvx. So we're going to get 2mvx. Everybody okay with that? You know what's right? This is the handout. We are going to do it together again here after. That's okay? So the momentum now, the change in momentum is 2mvx. Everybody okay with that? So if we know the momentum, right? What do we need to find the force exerted? Yeah? Force is what? ME, or you all remember this? Change in momentum over time.
Yeah.
Right. So all we need now is to get time. Okay? So here's what it said. Here's what it said. They said that the molecule has to travel a distance of 2L. I'm gonna show you what I'm talking about, right? The molecule has to travel a distance of 2L between collisions. So when the molecule starts here and it hits the wall here, before the next collision, it will travel a distance of L plus L, which is 2L. That's okay? Before it hits the next side of the wall. Right? Between collisions. So the first collision is, let's call it wall 1. Right? And then have to travel a next L before it hits wall 2. So it travels this is 2L. So how long will it take to travel 2L? Well, we know speed is distance on time. So time is distance on speed. So 2L divided by the speed it's traveling at. That's okay? So now that we know the time now, watch what I did. Right? Now that we know the time, right? Right? We found the time. Wait, hold on, yeah, distance over speed, that's the time taken. Now we know change in momentum is 2mvx and I divided by time. That's okay? Wait. And then if you do a little skills there, If you use a little math skills, you flip up the Vx, you'll get this. Right? What does that tell you? That tells you the force exerted by one particle on the wall. That okay? Kalina, correct myself. So that's one particle exerting that force, right? So what will be the pressure exerted by one particle? Pressure is what I'll tell you. Pressure is what? Force over area. So if I divide the force by the area, I will get the pressure exerted on the wall. Correct? So Daria, I know the force already, right? I know all that hard work there, and I find the force there. Can you find the area of the wall? Pardon me, L cube is the area. How you find area? Area.
Oh, sure, side by side.
So it's L squared, right?
Yes.
L squared, right? So the L squared will flip up here for all the math people. Pressure will now be equal to M squared Vx on L cube. That's okay? Wait, what is L cube? No, what is L cube? L cube is the area.
Get Darren said, so I said.
And that will not be so what L cube then? What L cube? L cube is what? The volume.
Oh gosh.
Right? So mvx squared on volume. So you'll see where the PV comes from.
No.
I'm bringing up P. So you'll get PV is equal to M.
And Vx squared.
Right. Good. But here's the problem. That is the pressure exerted by one particle. What will be the pressure exerted by n particles?
And
Multiply by n. Easy, right? Right? So I'm set it up there for you. Right? That's the pressure.
Oh, this is improved.
That's the truth. Yes. Right. Right? Now is the tricky part, right? Now is where we're going to consider. Now, right. Hold on, now I think I'm missing out. Look at it. So this is the pressure here of one particle. Now consider all the molecules in the container with x component of velocity. So remember, every particle will have a component of velocity, right? Remember, every component will have a component of velocity. So what shall happen? That make any sense?
No.
So this is
I mean, you're all serious, huh? No, making
right. So this here is the first particle. Correct?
Yeah.
There's the speed of the second particle.
Oh, okay.
Huh? Yeah. Summation of every single particle, right? So let me write it longer for you.
Velocity, same.
So the first particle was m Vx squared on volume, right? The second particle will be m Vx2 squared on volume, correct? The third particle will be the third particle will be the third particle will be m Vx cubed squared on V. And you go all the way down until you reach n particle. Correct? And all they did is they factor out m on V. See the little match there? Yeah? They factor out m on V.
I'm on L.
So L cube is V. L cube is V. Oh, it's slower. Right?
I'll do it.
Right, but here's the problem now, Marquis. We don't want to write all of that. We don't want to write all of this plus.
Wait, no. Don't tell me TMI is getting involved here.
Not really.
Okay.
But we can do it by induction, but you know. No, you might be able to. Yeah, you might be able to do that. Right? Anyway, so what you say, you don't want to have to write all of that. So instead, what they did is they found the mean. Right? Remember, so that symbol is mean, right? So they found the mean of the speeds, which is this here. Add up all the speeds and divide by n. That's okay? And if I bring up the n here, I know that n by the mean is this. So now, what's the cool thing now? I can take off this. And I can write n Vx squared. right? I can write n by mean squared. So now I know that in the x component of that in the x direction, I know that the pressure exerted is equal to mv by n mean squared. Right? You could write mean square like that, or you could write it like this, right? Some textbooks have it like this.
Mean square.
Yes, mean square. It's called mean square. Watch. And all this squared,
Oh,
and we find the mean,
oh
so
yeah.
it's called mean square. And I said that about 5 minutes ago.
I was listening to your 5 minutes ago.
Right? So this is for n particles in one direction. Right? Last thing,
Wait, wait. That was not one.
here comes C. Right? If we find the mean, sorry, if we find the average of all the directions, you gotta remember talking about the Pythagoras theorem thing,
Yeah,
right?
I listened down.
Right? This C squared represents a kind of average of not average, right? It represents the resultant of these three. Right? So C is the resultant of the velocity in x, y, and z direction. Right? Because you don't want to have to write x direction, y direction, z direction. So they simplify it and they find a resultant and we call it C. Right? And to further simplify things, here what they did. They said that each one of these speeds equal. So you end up with this being equal to this being equal to this. So you're going to get mean squared is equal to 3 Vx squared.
Mean square.
Yeah.
Maybe mean square is C.
Yeah, mean squared is same. So therefore the mean square is equal to 1/3 of Vx squared. And you're done. And you're done. Right? All you have to do after is this. Right? They all equal. They are all equal. Right? You replace Vx with 1/3 c squared, and we end up with this here. Carry across the L cube, and you'll get PV is equal to NM 1/3 V squared. Right? That's the objective of the whole group. Right? It's long here, it's a long group. Some questions just split it up in two.
We not a question on that.
Yeah, prove this. Yeah, watch. Yeah, ready? So here we gonna do now. We're gonna do it over. Right? But with your help. You will help me go through these steps. Here are my steps to remember. Right? Yeah, called direct handwriting horrible. Yeah, started people online now. Yeah, shouldn't do good. Shanita looking like handwriting a little bit. Then Shanita, between Shanita and Philly. One of them, handwriting, one of them come up here. All right, let's go. All right, so let's see if we can put it together, right? If you have, just do me a favor, write down 5 or 6 steps that we had to see. Number 1, find the force in one particle. See if you could write down your own steps to complete this whole thing.
Okay.
Steps alone, without looking back.
I will look back.
Huh?
I've been sideways.
Right? See if we can write down a few steps that we need. Write down the steps that you remember, right?
Why are you choose?
Write down the steps. In fact, I'm gonna help you. Right. Darian, I need a few steps, right? Number 1. What's his first step that you remember? Find the before you find the force, because you might remember how to find the force.
Momentum and time.
Change the momentum. Very good. Right? Find change in momentum. MV minus MV. Second thing, you can find the force. F is equal to MV minus MU on T. Yeah. Third thing is what? Find the after you find the force like 30 by 1. What you did? Now we didn't find it positive by many. No, we didn't find the volume. Find pressure. Pressure is equal to force on area. After that, what we did?
Acceleration. No, what?
Find acceleration anyway. Right? Right. Pressure for n particles. After that, what we did? So after we did n particles in one direction.
X, Y, Z.
Right. Then we did it in all three directions. Right? So these are the 5 steps that you technically have to take. That's okay? So, you feel you can do this on your own?
Yeah.
All right. Write down the 5 steps and then we're going to do it together. Right? I'm going over the proof again because it's important that we can actually do this, right? Write down 5 steps and let's move it out.
No.
All right. So how do we do this proof, right? So let's see if we can work it out. So step number 1, let's see if we can find the change in momentum. Let's see if we can find the change in momentum. Right? The change in momentum will be initial momentum, mvx, minus, remember, when it comes off the wall, the momentum is minus mvx. So we'll get 2 mvx. All okay with that?
Yeah.
Right? Right. Remember we need time, right? How we get time again, Jacob? How we get time? Right? So to get it time, we know that's what? Speed is distance sometimes. Time is what? Speed over distance, right? So what's the speed the particle moving with? Speed the particle moving with? Just Vx. And how long did it travel between collisions? Sorry? 2L, right? Between collisions. It started here, hit the wall before it collided again and traveled 2L. Right? So now to find the force is equal to change in momentum all on time. The change in momentum is 2mvx all over time. Time is vx on 2L. Okay? I'm just upside down. Or? Speed is equal to distance on time. Time is distance on speed. Yeah. Put it upside down. Tell me the wrong thing, right? Now, Jan, there goes the biscuit, huh? I was giving you a free digestive. I'm sorry there. Now, you say I said the wrong thing, right? Sorry. Right? This is 2L on Vx, right? The Vx will flip up and the 2's will cancel. So you'll get mvx all over, right? Just put this as a lower script, right? Subscript, I mean, Vx squared. Everybody okay with that? So here's where we have the force exerted by one particle, right? Moving in the x direction. What's the next step? The next step, Shazana, is to find the pressure. So we know pressure is equal to force over area. We know the force. We know the force. What's the area? L squared. The L squared will come up here, right? So you'll get mvx squared on L cubed, right? But I don't want to use that. I want to use V. So that'll be mvx squared all over V. Everybody okay with that? So that's the pressure exerted by one particle now, right? How do I get now the pressure exerted by n particles? Hi, Sharon, help me out there. So this is a one particle, right? So the pressure for n particles is what?
N by that.
No, yeah. This is one particle. It's not just n by this, so it's something that I have to do. So the first particle is this. Correct? The second particle is what?
Or average. The average.
The second particle is Vx1, 2 squared, right? The third particle is Vx3 squared on V until you reach the n particle. Right? Take out the M1 on V, right? And inside here, you will get Vx squared, Vx2 squared, this is Vx1, Vx3 squared, plus Vxn squared. That's okay? Right? So Jacob, I don't want to write this. What they did? They found the average. It's called the mean square, right? They found the mean square. Right? The mean square, I'll write it like this because the past papers have it like this as well. I want you to get used to all the forms. The mean square is this. Right? The mean square. This is mean, this is square. So the mean square is add up this. Right? You add it up and you divide by n. That's the mean square, right? Darian, when I reach here now, I want to replace this, right? So what to do? I want to replace this. But I have the mean square as this over n. What to do? Can you make this a subject of the formula? Can you make this a subject? Bring up the n. So until we'll get Vx squared multiplied by n to be this. That's okay? So if I take up this now, I can write this. Right? So we have taken up this here. You're seeing that? I'm taking up this and I'm writing this instead. So now I have pressure is equal to mass over volume by number of particles by mean squared in one direction. That's okay? This is volume, capital V. Everybody okay with that? So this is the pressure for n particles in one direction. Right? So I now reach here. What's the last step? This is pressure in one direction for all the particles. So I need what? Pressure in all three directions, right? So to make it simple, what they did, we're going to use this. We're going to use c squared is equal to bx squared plus by squared plus bc squared, right? Right? We're going to use the mean of all of this, right? The mean is like the average in all three directions. This here is the resultant, not the average. Instead of working in all three directions, I found the resultant. And the resultant is C. Right? Because it's three dimension, the resultant is bx squared plus by squared plus bc squared. Just like Pythagoras theorem in two dimension. Right? So now I know mean squared. Okay? If I assume that these are equal, I could say that mean square is equal to 3 by bx mean square. So watch this here. I can take off this here, carry the 3 on the side, and I can say that bx squared is equal to 1/3 over our mean square. So I'm going to take this off now. So this implies that pressure, I'm bringing up the volume, is equal to mn. I'm taking this off and I'm writing this. Right? And if you look at it, that is exactly what we were trying to prove. That's okay? You all look good up until here, and up until here.
Yeah.
Right. So here's what you have to remember, because this appears to confuse you a little bit. Please remember that a particle can move in three directions, right? It can move in the x dimension, the y dimension, or the z dimension. Okay? It can move in either three. But you don't want to have to write x, y, and z here. So what they did is they found the resultant of these three. So instead of three, the equivalent is just one resultant. That one resultant is C, right? This is C, right? So I found that C squared is equal to this plus this plus this, right? Add up all the mean squares and that's C, okay? To further simplify it, I said that each one of these equal. So 1 plus 2 plus 3 will give me 3 of this. I'm trying to replace Vx, so I carry across the 3, and I got Vx squared to be 1/3 mean squared. So I take off this and I put 1/3 mean squared. That's it. Okay? So that's a good sign if you're understand up until here, just here you have to go one little. Right? So go take a picture, write it down. Try and do it for yourself. Right? So that's phase 1 of the proof of our next part. Yeah. Because remember, any particles have energy, kinetic energy, we had to be able to find that. The kinetic energy of the particle. That one easier, but they will like that one. Guaranteed. I highly under.
That's it.
Okay, so we had to be able to do that proof and nice diagram will help you. Online, are you okay there? Katrina? Keelan? Right, so you gotta be able to do this, right? But I hear it, what about? If it's up. I know hear it. That's very good. What did you listen to? Come. Am I right, pencil?
Yeah.
Yeah. Oh yeah. Right, we have one more part of this proof. You understand what means? You understand what means squares? Mean square is what is. Now you're talking so much. What is mean square speed? What do you mean by mean square speed?
Yeah.
Save me wrong order, but okay. Right? So you're finding the mean of the squares, right? So you square all the speeds, add them up and divide by the total number, right? What do you think is root mean square? Very good, right? But I think that they like to ask that. Root mean square where you root the mean square, right? Think so, all right, okay. That's same thing for exams and you'll get it. Make sure you remember that. Make sure you remember that. Alright, so what's here? Please, excuse me. So what's here? Last thing, please. Here's what we need, right? I am adding a next formula here. PV is equal to 1/3 mn mean squared. Right? But I wanted to see something there. You're seeing this here? PV is equal to this, PV is equal to this, PV is equal to this. Can I do anything here? PV is nRT, PV is 1/3 nmc squared. Can I make them equal to each other? Yeah. So it means that 1/3 mn mean squared is equal to nkt.
If we are square,
Pardon me?
I didn't see it. Very good see.
Right. What will happen with the ends?
Can't love.
Right? And you'll get 1/3 m mean square is kt. Right? Question. I want to find a relationship for kinetic energy. How you find kinetic energy again? I have mv squared, right? So I have the m and the v squared. What do I have to do here? Put that to a half. How to do that? See that?
Yeah.
If I multiply both by 3 on 2, that will cancel. I'll get a half mc squared is equal to. So this is kinetic energy. So kinetic energy, this is average kinetic energy. Average kinetic energy is 3 on 2 kT. Does this formula make sense?
Yeah.
Temperature affects kinetic energy. Higher the temperature, the higher the kinetic energy. And that's a constant. Okay? So we found out that kinetic energy is proportional to temperature. Right? So we can add that here now. PV is equal, sorry. Kinetic energy is equal to 3 on 2 kT. All right? So now we're going to attempt some questions now using these relationships. Right? I won't do the proof. Again, I would like to know if any questions, but you have to be able to do everything there in black, right? All those steps. Right. By the way, if this formula is average translational kinetic energy, right? What will be total kinetic energy? If this formula gives the average kinetic energy, what will total be? Huh? Summation of C inclusive. So if this is the kinetic energy average for one particle, let's say, what will be the total? Multiplied by two, right? Right, so this is the ideal gas equation, right? We did everything on it. Now, taking all those formulas on the top right hand corner in blue, and we're gonna see if we can apply them. Excuse me. Good evening. Well, good. Right? So you'll recognize here part 1, 2, and 3 as the group, right? Part 3, they have the whole group. PV is equal to 1 to the MC squared, right? But I am not asking for that. I am only interested in part B. So I'll zoom in there. Those who can't see, you can log in, right? Let's try this here. Okay. And push that.
No, they're not doing it. I'm sleeping.
How does
that?
that?
Just signal.
I believe that. Come on, come on. Let's work this out. I don't know the year, whoever the year, right?
Like that.
Have we done? They have some mass, right? Chemistry people, how to find mass? Number of moles multiplied by the RMM, right? RMM. To find number of moles and then find the RMS speed and then see what will happen now. Come on, we still have 2 more to do. Serena, I get you. I get you. Which part 1? So you need to find number of moles. So which formula you will use? Look at the list up there. Can you choose? First one. PV and RT. Is it chemistry? Wait. Chemistry. Right? PV is equal to NRT. Right? So find number of moles and then what's the formula using the RMS speed, Jacob? What? What is RMS speed? Which formula? Yeah, out of all of those, which one? Last one have nothing to do with it. Second, the last one has with mean square in it, right? How many times I say what? Yes. I which one is the way you pick out? Yeah. Something part with Sam. What? And part 3. Oh yeah. Right, PV is equal to nRT, temperature must be in. Right, pressure is 1.6 by 10 to the 5. Yeah. Why Carl?
Yeah, you're the girl.
What do you want?
Yeah. Well, he didn't say it. Oh my God.
Online right, volume is what? Volume is 0.14. R is 8.31 and temperature is 4. How much you got? Huh?
6.9.
I told you two different answers. 6.74. Check. Right, and then the mass is the number of moles, or the chemistry people who are not doing chemistry, right? On those little things, right? Mass is equal to number of moles multiplied by RMM, grams per mole. RMM is the grams per mole. They give it out here. So it's 6.7 multiplied by 4 is how much?
6.9.
How much? 26. Okay, 27, right?
You can't say R because R is
Okay, all right. So molecular mass. That makes sense. I like that physics explanation. That's more physics. Okay, all right. What if? Right, nice. So molar mass, right? We'll go with molar mass. Okay, 27 grams of part 1, right? Part 2 here. Marquis, what's the point of part 2 again?
What? PV
PV is equal to nRT. And where again means mean square speed there. Mean square speed. What symbol is that?
PV
Equal to what?
NRT. Yeah.
PV equal to what? Hey, you can't use nRT. You want to get mean square.
PV equals 1/3 and mean square. Wait, they also mean square?
Yeah, they ask the mean square.
Where?
They ask the root mean square. So they get mean square first.
Oh, I see. How I see it's not R the F the S.
Square speed. Alright, so write it down. RMS means root mean square speed. We write it down. R. Root mean square speed, right? So therefore, mean square speed will be 3 by pressure by volume all over Nm. Right? 3 is 3. Pressure is 1.6 by 10 to the 5. The volume is 0.14. Do we know the number of particles? No. But we have the mass. The mass is 27 grams, which is 0.027. Right? We have a slight problem. We don't know the number of particles. How are we doing that?
That's fine.
How are we getting that? What's that the number of particles?
10 to the 23.
By
10 to the 23.
by what?
By moles.
By number of moles. Nice. So the number of moles is the number of moles is 6.74 and you multiply by Avogadro.
Avocado.
6.02 by 10 to the 23, right? Some more again. Please remember that this is the mean square, right? Okay, I'm write it down. Okay, do that, yeah?
Yeah.
Alright. Apa na like bago na lang.
Sige, copy lang.
I don't know. Copy down please, some way, yeah? Huh? Which one? Capital N? No, remember capital N is number of particles. So you form the number of particles by multiplying moles by Avogadro constant. Ready? Because with the mass kilogram, common N is number of moles, capital N is number of parts. Any answers online? They take a long to work it out. 6.15 by 10 to the minus 13. Live. Live. Yeah. Let's go, right? Let's go to I don't know how you can. Which one? Huh? Wait, log in here, so I'll get to you. Yeah, somebody else. Okay. I need it right now. So I have point. I got the same thing. Minus 30. Oh, I never get minus. What do we have? 6.15 by 10 to the minus 19. Right, but remember, Olya, what this is here? This is mean square, right? So to get the root mean square, we have to square root all of this. Okay, that'll be the root mean square. Seven point 84 by 10 to the minus 10 markings. I get well, I put in 6.15. Okay, well, I wrong the part, then you do what I have. MS minus 1, right? Yeah, mark up now. Oh yeah, Mark is in talking so much. What's the SI unit here for mean square? The SI unit for root mean squared MS minus 1. What's the SI unit for root mean squared? Sorry, the SI unit for root mean squared MS minus 1. What's the SI unit for mean squared? Okay. What is?
M squared is
Correct. Okay. Because it's the speed squared. Right? So you just square the SI unit. Right, you still have part 3 to do. Oh yeah. Still have one more to do, huh?
It's last time.
Enough time.
It really does.
We get it right now, but okay, I'll read that.
You know, it's even like an everyday understand.
No, but then it's not right.
You already ready, bro. Okay. You go on, right?
For what?
And you say what for an appetite is it?
Oh yeah, do part 3. Finish, hurry up, please.
I think it's pretty yesterday. What?
Yeah.
What's this? So, all you have. My God. Why would we do that?
Alright. So what the root mean square of oxygen? All that changes the what? All that changes the right? The molar mass, right? Go ahead, do it quickly. You can't do the whole thing again,
Yeah,
but with it.
yeah.
Oh yeah, please. I want to do one more question. Right, one thing that we didn't really get to practice is graphs. Every past paper has graphs, like there were 3 questions, they guarantee that in 2 graphs. Right, we had to spend some time practicing graphs, right? After we finish this, all we have to do is thermodynamics. Module 2. Oh wait, no, we're not done module 2, but I didn't give you all Hooke's law. Right, we'll do Hooke's law next. Yeah, we have to do Hooke's law and Young's module. Finish 1 and we're gonna finish 3. And we have next to do 2. So hopefully you might be doing 2 in school. Technically, when 2 done, you do everything. Right, so work out part 3. Work out part 3 quickly. What I have to do is switch the values, right? I tell you follow what to do. You have a calculator there, right? I am educating again. One. Will the number of moles change? Will the number of moles change? Yes, from the mass, right? The mass increase or decrease? Okay. So would it mean square, would it root mean square, increase or decrease? Okay. Okay, watch it and see that. What do you think, Daria? The mass will increase, so what would happen to the root mean square? Therefore, increase or decrease? Decrease, right? Decrease. Does it make sense to have a heavier particle moving a little bit slower? Right, so all those things is things that you should consider when you're working it out, right? So you know that you end up with that value. So I have send a value for part 3, please. Okay. You get area. Why is it 2.7? How much will I get? I got 2.78 by 10 to the minus 10. Right? I got 2.78 by 10 to the minus 10 meters per second, right?
Yeah.
Yeah?
Yeah.
Let's go again. So, already go, we are
Super easy.
on the 1 to 2. Check what I'm saying. Check what 10 class. Alright, so it did move a little bit slower, right? Right, the particles did move a little bit slower. Right, let's go again. Like I said,
Alright.
I might be able to speak that, but you can see this part here. It starts at pump. They give you the pressure, they give you the temperature, and the temperature rises, right? Calculating the pressure. If the volume kept constant. Whose law is that? Don't have to work it out, just tell me what to do. They kept the volume constant, so you're using pressure law, right? So you use pressure law there. In terms of kinetic theory of matter, why did the pressure increase? Jacob, why did the pressure increase? The cast iron pump has pressure. Why is it pumping air increase pressure? Huh? Pumping more air intense. You have more particles then? More particles, same speed, so you end up with more collisions.
Yeah.
Right? More collisions will give you greater pressure.
So that's gonna be different.
Okay, that's a form 5%. Yeah. Sorry, the volume kept constant, so that one is temperature increase the energy and it collide more. Sorry about that, but that's a form 5%. This one here a little blurry, so I might see that. That's the one that we just did. This one here,
Lay down on it.
right? You can't all of them because part of it is what we're doing tomorrow.
Nah.
Right, just really put part from find the number of moles. Everything you need there. I'll zoom in a little bit, right? You have pressure, you have volume, and you have temperature. Find the number of moles.
That question.
Pressure.
Yeah. Okay. 1.14.
That's the.
Yeah.
Yeah.
Make sure. Right, so just do my favor, make sure you have all these formulas here because I'm going to keep adding on more. Well, we're going to use these next day, right? And then we look at thermodynamics. If we can read up on that, that would be good. Right, and then we got questions combining all of these.